September 12, 1944. German airspace, 32,000 feet. Oberleutnant Kurt Welter, sitting in the cockpit of the world's first operational jet fighter, the Messerschmitt Me 262, felt confident as he watched the silver giants passing below him. With the raw power of his jet engines, he had been hunting the Allies' piston-engine escort fighters one by one. But these American B-29s were different. They were like ghosts, untouchable monsters gliding at altitudes where the engines of Germany's best piston-engine fighters would choke, where their flak batteries desperately clawed at the empty air. Even as Welter climbed towards them with the superior speed of his jet, there was something he didn't know. Hidden in the tails, wings, and fuselages of these massive aircraft was a defensive system that thought faster than a human brain, a network of mechanical intelligence. On that day, Welter would succeed in shooting down a B-29, but when German engineers gathered to examine the cold metal of the wreckage, they would finally understand that the war had already been lost. This is not just the story of an airplane. This is the story of how one industrial philosophy brutally crushed another. This is the story of how German engineering genius was rendered helpless when it collided with the unstoppable mathematics of American mass production, and how a handful of scientists, peering inside a metal box, saw not just wires and circuits, but the technological blueprint of their own defeat. It all began with the brutal reality of high-altitude warfare. In the early years of the war, American military strategists believed in a myth, the self-defending bomber. The theory was simple. Hundreds of B-17 flying fortresses, flying in tight combat box formations, bristling with machine guns, could penetrate German airspace without fighter escorts, strike their targets, and return. This theory was shattered in the bloody skies of 1943. During raids on targets like Schweinfurt and Regensburg, German fighters hunted these flying fortresses one by one. But inside that hell, there was an enemy more lethal than enemy bullets, the altitude itself. Imagine you are a B-17 waist gunner. The year is 1943. You are at 25,000 feet. The outside temperature is -50 degrees Celsius. A 300-mile-per-hour wind blasts through the open window, cutting your face like a razor. You are wearing layers of clothing and a bulky, electrically heated flight suit that keeps you alive but restricts your every move. Your oxygen mask is plastered to your face. Every breath is an effort, and the glass of your mask is constantly icing over. To shoot down an FW-190 flashing past you in seconds, you have to move a machine gun with frozen grease using your frost-bitten fingers. At this altitude, the slightest failure in your oxygen system leads to anoxia, loss of consciousness, and death within seconds. The nitrogen in your veins threatens to form deadly bubbles, a condition known as the bends. This isn't a combat mission. This is an hours-long struggle for survival at the very limits of human endurance. The American High Command knew that flying higher meant both greater safety and greater range, but the human body could not endure any more of this torture. They needed a new solution, a radical leap. This leap began in 1940, under the code name Project 345. The U.S. Army Air Corps envisioned a terrifying scenario: the complete fall of Europe, the loss of Britain, and America forced to fight a war alone from across 2 oceans. For this scenario, they needed a weapon that had never been imagined before, a superbomber capable of carrying a 9-ton bomb load over 4,000 kilometers at a speed of 640 kilometers per hour. The design Boeing presented was so ambitious that the B-29 Superfortress program became the most expensive and complex weapons program undertaken to that point. The Manhattan Project, which developed the atomic bomb, cost $1.9 billion. The B-29 program cost a staggering $3 billion, over $52 billion in today's money. America had decided that the key to winning the war was not just the nuclear weapon, but the platform that would deliver it to the target. And that platform would be a technological storm unlike anything the world had ever seen. At the heart of the solution was the technology that would end the hell of the B-17 crews, the pressurized cabin. Boeing engineers designed the aircraft's fuselage like a giant thermos. Pressurized air, bled from the aircraft's 4 engines, was pumped into the cabins through regulators. Thanks to this system, even as the plane flew above 30,000 feet, an altitude pressure of 8,000 feet was maintained inside the 3 separate crew compartments. For the first time in a bomber, pilots, gunners, and operators could sit in their shirt sleeves, fighting without fatigue on long missions. This was not just a matter of comfort. It was a strategic revolution that removed the human factor as the weakest link in the equation. The power to carry this beast to those altitudes came from 4 massive Wright R3350 duplex Cyclone engines, each producing 2,200 horsepower, more than the total power of a German Bf-109 fighter. Each engine was an 18-cylinder, air-cooled, turbo-supercharged marvel of engineering, delivering sea-level performance even in the thin atmosphere. However, this technological leap came at a terrible price. The B-29, in the words of General Curtis LeMay, head of the 21st Bomber Command, had as many bugs as the entomological department of the Smithsonian. As fast as the bugs got licked, new ones crawled out from beneath the cowling. The biggest problem was the engines. The R3350S were so powerful that they constantly overheated, especially when taking off at maximum weight from the hot, humid runways of the tropical islands. Making the problem worse, the engine's crankcase was made of magnesium to save weight. Magnesium was light, and it was strong, but it was also highly flammable. When an engine fire started, it turned into an inferno reaching 3,100 degrees Celsius. This heat could melt the aircraft's main wing spar in seconds, causing the wing to shear off. On February 18, 1943, the second prototype crashed over Seattle due to an engine fire, killing Boeing's chief test pilot, Edmund Allen, his 10-man crew, 20 workers in a meatpacking plant on the ground, and a firefighter. The statistics were brutal. Of the 414 B-29s lost during the war, 147 were lost to enemy fire, while 267 were lost to engine fires and mechanical failures. Its own aircraft was deadlier than the enemy. These problems culminated in an industrial crisis known as the Battle of Kansas. In early 1944, hundreds of B-29s rolling off the production lines at Boeing's Wichita plant were not airworthy. Production had been so rushed that the planes were riddled with flaws. General Hap Arnold personally intervened, sending thousands of experienced workers from other factories to the modification centers. For 5 weeks, these teams corrected over 568,000 faulty electrical plugs, made dozens of changes to the engines, and literally rebuilt the aircraft. They finally made 150 planes combat-ready. This was not production, it was a rescue operation. It was this mixture of technological nightmare and industrial miracle that appeared like a ghost before the Germans. Luftwaffe pilots repeatedly expressed the same helplessness in their reports. Above 30,000 feet, their Bf-10-9s slowed as if climbing a wall, and the engines of their FW-19s choked in the thin air. In desperation, the Germans formed units known as the Sturmböcke, battering rams. These FW-19s were equipped with extra armor plates and 30mm cannons. Their mission was to dive into the bomber formations, fire at the closest possible range, and if necessary, as a last resort, ram the planes. This was not a tactic. It was an honorable suicide. Focke-Wulf engineer Kurt Tank designed the legendary TAR-152, capable of climbing to 47,000 feet. But these planes entered the war too late, and in such small numbers that they never posed a threat to the B-29s in the Pacific. Even rocket-powered marvels like the Me-163 Comet, with only a few minutes of fuel, could only flash past these silver giants for a moment. The B-29 was the new king of the sky, an untouchable ghost. The German High Command knew that the only way to defeat this ghost was to understand it. If they couldn't hunt it, they had to steal its secrets. The wreckage of a B-29 was not just an intelligence victory, it was a technological treasure that could change the course of the war. They just needed one chance. And one day that chance fell from the sky in the form of a B-29, sputtering with damaged engines, descending towards a field in German-controlled territory. As German soldiers approached the silent silver giant with a mixture of fear and awe, engineers and scientists were already on their way from Berlin. The legendary machine they had read about in reports, the one their pilots spoke of with despair, was finally in their hands. This was not just the wreckage of an airplane. This was Pandora's box. And the Germans were eager to open it. But when they opened that metal box, what they found would not just be a weapon. What they found was the technological blueprint of their own defeat. So, what was inside that box? As German soldiers approached the silent silver giant with a mixture of fear and awe, the brightest minds from the Luftwaffe's test center at Rechlin and Berlin's secret laboratories were already on their way. The legendary machine they had read about in reports, the one their pilots spoke of with despair, the one that appeared for a moment in the sky, was finally in their hands. This was not just the wreckage of an airplane. This was an opportunity to steal the fire of Prometheus. This was Pandora's box, and the Germans were eager to open it. When the wreckage was brought under tight security to the test center, the attitude of the German engineers was one of confidence. This confidence was not misplaced. They were the engineers who had created Werner von Braun's V-2, the world's first ballistic missile, and unleashed Messerschmitt's Me-262, the first operational jet fighter, into the skies. They had imagined and brought to life aircraft like the Fieseler Storch, capable of vertical takeoff, and the flying wing designs of the Horten brothers. What secret could a simple American bomber hold against their genius? For them, this was an American machine built with brute force, suitable for mass production but lacking in subtlety. Initial inspection seemed to partially confirm this prejudice. The aircraft's massive dimensions, its 43-meter wingspan, its 4 engines, each nearly the size of an automobile, showcased the brute force of American industry. But when they looked closer, the first moments of astonishment began. The surface of the aircraft was as smooth as a mirror. The protruding rivet heads, standard on German aircraft, had been replaced by a completely flush riveting technique. This was not just an aesthetic detail. It was an engineering detail that reduced drag, increasing the aircraft's speed and range, and was incredibly difficult and time-consuming to mass-produce. To be able to standardize such precise workmanship on thousands of aircraft during wartime was something the Germans couldn't even dream of. The aluminum panels of the aircraft were not overlapped, but butt-jointed, joined edge to edge. This was aerodynamically perfect, but a production nightmare. The Americans had standardized this nightmare. When they went inside, their astonishment grew. The pressurized cabin was a complex system of pipes, valves, and regulators. But the real revolution was designed for the gunners. The famous windy waist gunner positions of the B-17 had been replaced by calm, quiet, and warm plexiglass blisters. The gunners sat here, in the comfort of an office. But where were their guns? The guns were inside aerodynamic turrets, scattered across the aircraft's fuselage. So how did the gunners control these guns? The answer was hidden in the heart of the aircraft, inside an armored metal box, the Central Fire Control System, CFC. When the German engineers opened this box, the moment they understood the course of the war had arrived. Inside, they didn't find the precision Zeiss optics, mechanical gears, and cams they expected. Before them was an electronic labyrinth of hundreds of vacuum tubes, military-grade gyroscopes from Sperry, complexly wound servo motors, potentiometers, and kilometers of cables. This was not a weapon part. This was a supercomputer of its day, squeezed into an airplane. This was an analog computer. German engineering genius was at its peak in the fields of mechanics and optics. But what they faced was something from a completely different philosophy. This was the military monster that America's massive pre-war consumer electronics industry, giants like RCA and General Electric, which produced millions of radios, refrigerators, and telephones, had become. The way this system worked was like science fiction for the Germans. When a gunner placed his eye on a periscope-like sight, he was not looking at a weapon, but at a series of sensors. The moment he kept the target in the center of his viewfinder, the system's brain, the General Electric M-series analog computer, started working. This mechanical brain, without digital chips, using entirely moving parts and electrical signals, performed a series of calculations at an incredible speed. First, thanks to the gyroscopes, it detected the speed and instantaneous movements of its own aircraft, the B-29. It factored in the plane's yaw, dive, and climb into the equation. Then, from the speed at which the gunner was tracking the target, it calculated the enemy aircraft's speed and direction with incredible precision. But this was just the beginning. The computer also had to account for all the other invisible forces that affected ballistics. It added gravity, which determined how much the bullet would drop before reaching the target. It accounted for air density, which would slow the bullet down as the altitude changed. And most importantly, it calculated the deflection angle, or lead, which determined how far ahead the bullet needed to be fired due to the relative motion of the two planes. Combining all these variables, the computer found the perfect angle for the bullet to be fired from the barrel in less than a second. The result was not sent to the gunner, but directly as an electrical signal to the servo motors that moved the turrets in different parts of the aircraft. The gunner just tracked the target. The machine did the rest. This wasn't a weapon. It was a prophecy machine. It didn't calculate where the bullet should go, but predicted where the target and the bullet would meet. The flexibility of this system was even more terrifying. The top gunner, acting as the fire control officer, could manage the system like an orchestra conductor. If 3 fighters were attacking the plane from the right, he could instantly transfer control of not just his own turret, but also the bottom and top turrets to the right side gunner. A single gunner could create a wall of fire from 3 turrets, meaning 6.50 caliber machine guns. This was not the defense of a bomber, it was the firepower concept of a warship. German engineers studied this system for days, for weeks. They drew out the schematics of every vacuum tube, every circuit. They understood the working principle in theory. But the more they understood, the more their horror grew. What they were facing was not just a clever design. It was the product of an industrial capacity they didn't have, a production philosophy they didn't have, and resources they didn't have. This box showed them not just a technological secret, but also the unbridgeable gap between them. Their best optical factories had been turned to rubble by Allied bombing. Their best engineers were trying to create miracles with scarce resources like synthetic fuel and recycled metal. But the Americans, as if they had come from another planet, were producing tens of thousands of these complex electronic brains as if they were making sausages. In that cold hangar at Rechlin, the German engineers saw not just the parts of an airplane, but the limits of their own industrial civilization. Could they copy this box? Maybe. With years of effort, by bringing together their best scientists, they could build one prototype in a laboratory. But could they produce tens of thousands, install them in thousands of planes, and keep them running on an island in the middle of the Pacific? The answer was as clear and brutal as the complex circuits inside that metal box. Never. The question was no longer, how do we understand it? The question was, do we have a Germany or even a world to produce this? And at that moment, in that hangar, they understood that the war was not won just with courage or tactical genius, but also with the smoke coming from the factory chimneys, with the speed of the assembly lines, and with the total production capacity of a nation. They had ripped out the heart of the beast, but what they saw inside was the warrant for their own death. In that cold hangar at Reich, the German engineers saw not just the parts of an airplane, but the limits of their own industrial civilization. They had ripped out the heart of the beast, but what they saw inside was the warrant for their own death. After weeks of meticulous work, the report summarizing their findings made its way to the Reich Air Ministry in Berlin. This report was not a technical analysis. It was a eulogy from one civilization to another, and a death notice for their own industry. The summary of the report was based on a single, brutal truth. The problem was not understanding this American system. The problem was that a Germany capable of producing it no longer existed. To understand this admission, one must understand the fundamental difference in the two nations' approach to war. This was not just a war of engineering, but a war of philosophies. The philosophy of German industry was craftsmanship perfection. The best example was the Tiger tank. The Tiger was more than a war machine. It was a moving fortress, an engineering masterpiece. With its nearly impenetrable armor, its deadly 88mm gun, and its flawless optics, it could destroy anything it faced on the battlefield. But each Tiger was almost handmade. Its production was incredibly slow, complex, and expensive. Each one required weeks of labor from master craftsmen. The result? Only 1,347 Tiger I tanks were produced throughout the war. The Me-262 jet was a product of the same philosophy. Revolutionary, deadly, but too few, and too late. German genius was masterly at creating a few, nearly perfect weapons. The American philosophy was completely different. Overwhelming mass production. The symbol of this philosophy was the M4 Sherman tank. The Sherman, in a one-on-one fight with a Tiger, had almost no chance. It was a tank with weaker armor and a less powerful gun. But that didn't matter, because for every one Tiger tank, the Americans produced 50 Shermans. Nearly 50,000 Sherman tanks were produced throughout the war. The Americans didn't aim for perfection, they aimed for good enough, and then they produced so much of it that the enemy drowned in this steel flood. The record of building a Liberty ship in 4 days and 15 hours at Henry Kaiser's shipyards was the pinnacle of this philosophy. The point wasn't to make the best ship, the point was to fill the ocean with ships. The B-29's gunsight computer was where these two philosophies collided. The German engineers approached it like a Tiger tank. How can we produce this masterpiece? The Americans, on the other hand, had approached it like a Sherman tank. How do we produce tens of thousands of these? And the answer to that question lay in something the Germans could never have: a massive industrial ecosystem. The first layer of this ecosystem was the subcontractor network. The B-29 was not built by a single company, but by an entire nation. Over 1,400 different companies were involved in the project. These were not just aviation companies. The companies that sold you and your family sedan cars before the war were now producing the most complex weapon of the war. The Hudson Motor Car Company in Detroit produced over 800 B-29 rear fuselages and wing panels. General Motors' Fisher Body division manufactured thousands of engine cowlings and tail sections. And most importantly, Chrysler, which built a massive factory in Chicago, was tasked with producing the B-29's troublesome but powerful R3350 engines. Frigidaire stopped making refrigerators and started producing the B-29's giant propellers. This was a nation directing all its industrial power towards a single goal. In Germany, on the other hand, industry was constantly being disrupted and trying to reorganize under Allied bombing. The second, and perhaps most critical layer of the ecosystem, was the raw material empire. One B-29 required about 12 tons of aluminum, half a ton of copper, and kilometers of cables. America had almost unlimited access to these resources. The iron ore from Minnesota's Mesabi Range, the coal beds of Pennsylvania, and most importantly, the cheap and abundant electricity provided by the massive hydroelectric dams of the Tennessee Valley Authority. Without these dams, aluminum production would have been impossible. An air force without aluminum was unthinkable. To win the war, America had built not just factories, but also the dams to feed those factories. Germany, on the other hand, was living in a hell of resource scarcity. Despite Albert Speer's miraculous organization, Germany was dependent on synthetic fuel, recycled metal, and iron ore from Sweden. The critical electronic components needed for the B-29's gunsight computer, such as copper and tungsten, were worth a treasure. The Allied raids on the ball-bearing factories in Schweinfurt were a dagger plunged into the heart of German precision industry. While the Germans were trying to create works of art with their limited resources, the Americans were creating an avalanche with unlimited resources. The third layer of the ecosystem was people. The Rosie the Riveter poster was not just a propaganda tool, it was a symbol of a reality. Millions of American women who were housewives before the war, who had never worked in a factory, were transformed into skilled workers in a few weeks of training, flawlessly driving thousands of rivets and soldering complex electrical circuits. This was the power of a free society, mobilizing for a common cause. Germany, on the other hand, was becoming increasingly dependent on slave labor and forced laborers to keep its industry afloat. This was not just a moral collapse, but also an inefficient system. The productivity of a motivated, well-fed and well-paid American worker was many times greater than that of a slave laborer working in fear. But the most overwhelming truth that the German engineers began to understand in that hangar at Rechlin was even beyond this industrial ecosystem. This was the philosophy of logistics and maintenance, known as the system of systems. The Americans had not just planned to produce the B-29, they had designed the aircraft's entire life cycle. Each B-29 came with hundreds of pages of incredibly detailed maintenance manuals. Everything from how to tighten a screw on the engine to how to calibrate the gunsight computer was explained step by step, with illustrations. These manuals were designed to turn a farm boy from Iowa into a technician capable of maintaining one of the world's most complex aircraft on an island in the middle of the Pacific, with just a few months of training. America had established massive training schools that graduated thousands of technicians. And then there was logistics. American logistics was a weapon in itself. Imagine a B-29's gunsight computer malfunctioning during a mission on the island of Tinian. The technician diagnoses the faulty module. A request form is filled out. This request crosses the Pacific via radio waves, reaches Hawaii, and from there, San Francisco. A new computer module is taken from the warehouse of the General Electric factory in New York. It is loaded onto a plane, flies across the country, crosses the Pacific, and within a few days is installed in that B-29 on that small coral island. This was an operation that was unimaginable in an era when Germany was struggling to deliver fuel to its tanks on the Eastern Front. Even if the Germans could have copied a B-29 computer, they could never have copied the massive support system that kept it running. When the engineers at Rechlin looked at that metal box, they didn't just see vacuum tubes and circuits. Inside that box, they saw the automobile factories of Detroit, the dams of Tennessee, the training schools in Iowa, and the cargo planes taking off from San Francisco. They saw the unstoppable industrial power of an entire nation locked on a single target. And they understood that the reason they were losing this war was not because their soldiers were not brave enough or their engineers were not smart enough. The reason they were losing this war was because their philosophy was wrong. While they were trying to forge a few perfect swords, the Americans had produced an avalanche of swords. And it was inevitable that they would be buried under that avalanche. But the final act of this story, the most concrete and unexpected proof of this overwhelming truth, would be written not in Germany, but thousands of kilometers away, in the lands of America's other great rival. The Soviet Union had achieved what the Germans could only dream of. They had captured working, intact B-29s. What they would do with these planes would be the final proof of the victory of American industrial philosophy. The final verdict of the war would be delivered not in the ruins of Berlin, but in the design bureaus of Moscow, while the German engineers in that cold hangar at Rechlin were reading the blueprint of their defeat. Thousands of kilometers away, in Moscow, the most ironic and illuminating act of the war was unfolding. The Soviet Union had achieved what the Germans could only dream of. 3 American B-29 Superfortresses, damaged during the war and making emergency landings in the nearest safe territory, Siberia, were a perfect prize in Stalin's hands. When America asked its ally, the Soviet Union, for the planes back, Stalin's answer was an icy silence. These planes were not coming back. They were to become the future of the Soviet Union's strategic aviation. This was the ultimate test of what the German engineers had deemed impossible. What could the Soviets do with 3 working, completely intact, state-of-the-art aircraft in their hands? The answer came from Stalin, and it was brutally simple. Copy it. With this order, the largest and most audacious reverse engineering operation in aviation history, codenamed Project B-4, began. The 3 B-29s were brought to the Tupolev Design Bureau in Moscow. One was left untouched, as a reference. One was used for flight tests and pilot training. The third was taken to a hangar to be completely disassembled, down to the smallest screw, the thinnest wire. Over 900 factories and research institutes were involved in the project. Within 2 years, the Soviet industry was tasked with producing 20 copies of this American marvel. At the head of the project was the brilliant designer Andrei Tupolev, and the pressure on him was immense. Failure meant a one-way ticket to Siberia. At first, the task seemed simple, but when the Soviet engineers got to work, they came face to face with the same unbridgeable gap that their German colleagues had understood in theory. The first problem seemed simple, but insurmountable: units of measurement. The Americans used the imperial system. The Soviet industry was based entirely on the metric system. The aluminum skin of the B-29 was 1/16 of an inch thick. Soviet factories did not produce a sheet of this thickness. The closest metric equivalent, 1 millimeter, was too thin, and 2 millimeters was too thick. This was not just a sheet metal problem. It was a problem that completely affected the aircraft's weight, balance, and aerodynamics. Just for this reason, the Soviet engineers had to redraw over 105,000 technical drawings to match their own industrial standards. This was not copying. It was a recreation. Each part turned into a nightmare. Even the chemical composition of the aircraft's approximately 14 kilometers of electrical wiring was different. The Soviets had to mobilize their chemical institutes to develop a similar insulation material. The B-29's famous analog computer was a black box for the Soviets. They tried to copy it, but their own electronics industry was so far behind that they eventually gave up and decided to use a simpler American radio found in the B-25 bombers they had received through Lend-Lease. Instead of the Reich R-3350 engines, they had to adapt their own Shvetsov ASH-73 engines. With every step, they were painfully experiencing how far ahead American industry was. After years of feverish work, in 1947, the Tupolev Tu-4 was born. At that year's Tushino Air Show, Western military attachés, watching the parade, saw 3 familiar silhouettes. They smiled at each other and took notes. The Soviets are finally showing the B-29s they captured. But minutes later, when a 4th B-29 appeared on the horizon, the smiles froze and a silence fell over the stands. They understood at that moment. The Soviets had copied the B-29. This was one of the moments that started the Cold War. The Tu-4 became the Soviets' first intercontinental nuclear bomber and for years posed the biggest threat to the West. However, the real lesson of this story was this: even a giant industrial power like the Soviet Union with 3 perfect working examples in their hands, had to declare a national mobilization and spend years to copy this aircraft. This was the final proof of the impossible situation the Germans were in. The Germans had neither a single intact B-29 nor the massive resources that the Soviets possessed. The 2-4 project was a monument to how far American industrial philosophy had left not just its enemies, but even its allies behind. When the war ended, this bitter truth echoed in the statements of the defeated German leaders. The once mighty figures, sitting before Allied interrogators, no longer sought the cause of their defeat in tactical errors or the cowardice of their soldiers. They all said the same thing: production. Albert Speer, the Minister of Armaments of Nazi Germany, said in his interrogation, "Our fundamental mistake was to approach the war with the meticulousness of a craftsman. We wanted every weapon to be the best, the most perfect. The Americans, on the other hand, adopted a completely different approach: simplification, standardization, and mass production. While we were producing 1 Tiger tank, they were producing 10 Shermans. In the end, their good enough quantity crushed our perfect quality." The legendary commander of the Luftwaffe, Adolf Galland, was even clearer in a post-war interview. "Fighting against the B-29 was like trying to resist a technological storm with an umbrella. Our jets might have been faster, but they had connected everything into a system. Their gun sights, their engines, their production lines, all served a single purpose: overwhelming superiority. We were making wonderful weapons one by one, like craftsmen. They were producing the future from an assembly line. When I heard about that gun sight computer, I understood that we were not just fighting against an airplane, but against an entire industrial philosophy. And the victory of this philosophy was hidden in the ruthless language of numbers. This was not just a war, it was a statistical massacre. Now, let's see the dimensions of this steel avalanche. Throughout the war, America produced a total of 3,970 B-29 Superfortresses, nearly 4,000 silver giants, each a flying fortress. Each aircraft consisted of 600,000 rivets, about 14 kilometers of electrical wiring, and over 55,000 different parts. This was an engineering miracle, repeated 4,000 times. Boeing's Wichita factory, at its peak, was producing 16 of these complex machines a day, meaning 1 B-29 every hour and a half. This was just one factory. The massive facilities of Bell in Marietta, Martin in Omaha, and Boeing in Renton, and thousands of subcontractors worked day and night to feed this steel avalanche. They were not just producing airplanes, they were mass-producing victory. The number of .50 caliber rounds produced for the B-29's firepower was beyond imagination. Throughout the war, America produced billions of .50 caliber rounds. In the last quarter of 1943, American factories were producing 522 million metal bullet belt links a month. Imagine that number, over 500 million a month. This was not just a military operation, it was an avalanche of steel and lead. And the human factor? Throughout the war, America graduated hundreds of thousands of pilots. Each P-47 pilot received at least 400 hours of flight training before going to war. In this training, they learned to fly different types of aircraft, to fly with instruments, formation flying, and most importantly, to practice shooting with live ammunition. Towards the end of the war, a German pilot sent to the front had less than 100 hours of total flight time. On one side, there were well-fed, well-rested pilots who had trained for months in the best conditions. On the other, there were young men thrown into the sky in desperation, without enough fuel to fly properly. This was not a war, it was an execution. In the end, German engineers could design the most complex weapon systems. Their pilots could be the bravest, but none of them could defeat an industrial giant that produced a new Thunderbolt every hour at a factory in Farmingdale. completed 16 B-29s a day in Wichita, cast hundreds of thousands of engines in Chicago, and pressed 30 million rounds a month in Lake City. Let's end the story through the eyes of that Me-262 pilot from the beginning, Kurt Welter. His individual courage and the technological marvel he flew were a symbol of German genius, but his victory was a meaningless detail. Because while he was shooting down a single B-29, the unstoppable steel avalanche, created by millions of anonymous workers in factories tens of thousands of kilometers away, was already on its way. Welter had hunted a single ghost in the sky. But behind that ghost, an entire army of ghosts was coming. And the power of that army came not from the horsepower of its engines or the intelligence of its gun sights, but from the system itself that created it. When the German scientists examined that B-29 wreckage, they discovered not just the secrets of an airplane, but also the new and brutal reality of 20th century warfare. The winners of wars were no longer just the best warriors, but also the best factories. And on that day, inside that metal box, they saw the silent, mechanical, and unstoppable victory of American industry. Victory was not just of an airplane, but of a production philosophy, of a system, of a civilization. That box was whispering to them that they had already lost the war.